Okay, so now we've looked at being able to add and being able to subtract two equations to eliminate a letter. We're now ready to look at the full extent of simultaneous equations. So you'll notice with this first set of simultaneous equations, there's no way we'll get rid of either of these letters by adding or taking them because they're not the same. That has to be a 3y in order for us to be able to add or take them. Well, I can actually make that a 3y by timesing the whole thing by 3. If I times that by 3, I end up with 12x minus 3y, and times that by 3, 45. Now, I've not had to alter the other one because I already said 3y. So in order to get rid of these 3y's, as I pointed out in the previous lesson, if these signs are the same, then it's a subtraction. That was lesson 2. If these signs, as they are, different, then that will be an addition. So if I add these two together, I get 14x. If I add these two together, I get 0, because minus 3y add 3y is nothing. And if I add these together, I get 56. Now, you're not expected to know your 14 times table, but if you go through your 14 times table, you'll realise that that goes into that 5 times. So x equals 5. Now if we go back to the original 2, as we always do, I'm going to go into this equation because it's all plus signs. So 2 5s, 10. Plus 3y equals 11. Put the 10 on the other side, becomes a take 10. So 3y is equal to 1. So y is equal to, and because that's not in your 3 times table, we divide by 3, y is equal to 1/3. So part B. A second one, and once again, I can make that the same as that by timesing that top one by 3. So if I times that top one by 3, I get 9a, add 3b equals 30. I haven't had to do anything with this one because it already says 3b, so 4a add 3b equals 10. Now it doesn't matter that I've got different letters to the x and y, as you probably appreciate from the previous worksheets. It's solved exactly the same way, and just that we tend to use x and y a lot. Now here we've got 3b and another positive 3b, so as in previous lessons, if we subtract them, the 3b's will disappear. 9a take 4a, on the other hand, is 5a. As I've said, 3b take 3b, gone. And 30 take the 10, 20. Now if I go through my 5 times table, a works out to be 4. Now if I go back to the original, it's probably best to put it into that one. So a is a 4, so 3 4s is 12, plus b equals 10. Move the 12 across to the other side, becomes a take 12, and 10 take 12 is minus 2. Now you notice that was much easier than the first question. The thing is though, the method is exactly the same every time. The difficulty comes with if you have a negative answer, or what made the last question more challenging, when you have a fractional answer. But the method that you follow is identical each time. In this case, we times that equation by number. In this case, we then subtract the equations, but then you always end up putting that first answer back into one of the equations to solve for the other letter. The steps are always the same. So again, I can make that 2q the same as that by timesing it by 2. So if I times that top equation by 2, I end up with 10p, end up with 4q equals, and times by 2, 28. The second equation we do not need to alter because that already says 4q. And as pointed out with previous ones, positive 4q, so we subtract. 10p take 3p is 7p. They disappear, that's why we subtract them. And 28 take nothing is quite simply 28. That belongs to the 7 times table, so p works out to be 4. It doesn't matter which one you put it into. This second one has the easier numbers. So if I put 4 into there, 3 4s, 12, plus 4q equals nothing. If I move the 12 across, it becomes a minus 12. And since there's nothing there already, it's minus 12. Now 4 goes into 12 3 times, but it's minus 3 times for this question. That's our answer. So for most exam papers, that is how we would deal with each situation. However, occasionally they'll have a question set up like this, where it doesn't look so easy to make those the same. However, you can make this letter the same. And you can do that. You don't always have to eliminate the second letter. You can eliminate the first letter. So if I was to use the same process as in the previous examples, if I times that first equation by 5, I've made these letter x's the same. So 5 times x is 5x, minus 5 times 5, we've got 25y, and 5 times the 14 is 70. We haven't had to do anything with the second equation. And then in order to get rid of the 5x's, I need to subtract them. Now this is a bit more challenging. Yes, 5x take 5x, nothing. But minus 25y take minus 2y. Minus makes that a plus 2y, but we end up with minus 23y. 70 take 1 is 69. Now 23 goes into 69 3 times, but we've got minus 3. So we've got y this time. Put that into one of the equations. I'm going to go into this top equation. So we have x. Now, your gut reaction is to write the minus sign, but when I put minus 3 into there, 5 times 3 is 15. 5 times 3 is 15, but it was a minus. So we think to write minus 15. There's already a minus sign there, and we know a minus times a minus is a plus. Now if we take the 15 across the other side, it becomes a take 15, so we end up with minus 1, so x works out to be minus 1. So there is a pretty challenging example. You may want to rewind that one and watch it again. You don't always get one that difficult, but they do exist occasionally. Okay, we'll look at one more. So in this particular setup, it would be easier to times that one by 2. So that would give us 4x minus 6y equals 18. Therefore, with the 1 underneath it, we're able to eliminate the y's by adding the two equations because they're both different signs, as I pointed out previously. So therefore here we would get 9x, and here, adding these together, we get 27. That belongs to your 9 times table 3 times. So if I put 3 into either of these, now they look like smaller numbers, I just don't like minus signs. So if I can avoid it, I avoid it. So I'm going to put it into there. 5 3s, 15. Add 6y equals 9. If I move the 15 across to the other side, it becomes a take 15. 9 take 15 is minus 6. Now 6 goes into 6 once, but there's a minus